Hello, welcome to my video series of data structures. This is part 5 of module 6, the heap data structure. In this video, we will discuss binomial queue. In the previous video, we explored two merge-efficient heap data structures, the leftist heap and the skew heap. These data structures reduce the time complexity of the merge operation to O log n, an improvement over the O(n) time complexity of a binary heap. However, the time optimization comes at a cost. The time complexities for the increased key and decreased key operations increased from O log n to On. In some applications, the values of the data elements are frequently updated. For instance, recall the example of using a heap to maintain a dynamic set of video games and their ratings, which allows us to efficiently identify the highest rated game. In practice, completing a game often takes time, making a slower find best operation more tolerable. However, game ratings can fluctuate frequently, especially when patches or updates are released. In such cases, it becomes crucial to perform increased key and decreased key operations efficiently. To address this need, we introduced the binomial queue data structure. In a binomial queue, the merge, increased key, and decreased key operations can be performed in O log n time. However, this comes at the cost of increasing the time complexity of the find best operation from O1 to O log n. Notably, all fundamental operations in a binomial queue run in O log n time, except for the construct operation, which can be completed in On time. Let's begin by introducing the concept of a binomial tree. The structure of a binomial tree is defined by its height k. Let Bk denote a binomial tree of height k. When k equals to 0, the binomial tree consists of a single node. When k is greater than 0, a Bk tree is constructed by attaching one Bk-1 tree to the root of another B'K-1 tree. For example, the leftmost tree, with only one node, is a binomial tree B0 of height 0. A B1 tree is formed by concatenating two B0 trees. For example, the middle binomial tree B1 is created by attaching the blue tree B0 to the root of the orange tree B'0. Similarly, the right B2 tree is formed by attaching the blue tree B1 to the root of the orange tree B'1. Note that, according to this construction rule, a binomial tree node can contain more than two children. Therefore, a binomial tree is not necessarily a binary tree. Binomial trees also satisfy the heap order property. In a max heap, each node in a binomial tree is greater than or equal to its children, ensuring that the best data element always locates at the root. Therefore, each binomial tree is a valid heap. Based on the definition of binomial trees, we can identify two important properties. First, the height of a binomial tree, Bk, is k. Second, the size of binomial tree doubles each time its height increases by 1. Hence, the size of binomial tree Bk is 2 to the power of k. Having defined binomial trees, we now introduce binomial queues. A binomial queue is a forest that contains a collection of binomial trees. In a binomial queue, there can be at most one binomial tree of any given height k. For example, as shown in the slide, a collection containing a B0, a B1, and a B3 tree forms a valid binomial queue, since no two binomial trees share the same height. It is also possible that a binomial queue omits certain heights. For instance, the binomial queue shown here does not contain a B2 tree. However, a collection with two B1 trees and a B3 tree would not form a valid binomial queue, because it contains two binomial trees of height 1. The relationship between the size of a binomial queue and the binomial trees it contains can be better understood through binary representation. The binary representation of a binomial queue contains m digits if the largest binomial tree contained in the queue is Bm. For each binomial tree Bk in the queue, the kth digit in its binary representation is set to 1. Know that we refer to the least significant digit in the binary representation as the 0th digit. For example, the binary queue shown here contains three binomial trees, B0, B1, and B3, corresponding to the binary representation 1, 0, 1, 1. This binary representation directly reflects the size of the binomial queue. The binary representation 1011 evaluates to 11 in decimal, which matches exactly the size of this binomial queue. This property holds because a binomial tree Bk contains 2 to the power of k elements, aligning with the weight of the kth digit in binary numbers. Since any decimal number can be represented in binary, a binomial queue can be constructed for a dataset of any size. From the above argument, we can conclude another important property of binomial queues. A binomial queue with n data elements can contain at most O log n binomial trees. The height of the largest binomial tree is also bounded by O log n. This is because the number n can be represented using O log n binary digits, with at most O log n occurrences of the digit 1. Now, let's move on to discussing the fundamental operations of binomial queues. First, consider the find best operation. Recall that each binomial tree is a valid heap, meaning that the best element in any binomial tree is always located at its root. Therefore, the best element in the entire dataset must be found at one of the binomial tree roots. Note that the roots of the binomial trees are not sorted by their values, and their orders are arbitrary. For example, as shown in the slide, each root is a potential candidate for the best element. To find the best element, we need to examine all roots. Since a binomial queue with n data elements can contain only O log n binomial trees, examining each root takes O log n time. Thus, the find best operation runs in O log n time in a binomial queue. Next, let's discuss the merge operation. The process of merging two binomial queues is analogous to the standard method of adding their binary representations. Starting from the smallest binomial tree, we iteratively merge binomial trees of the same height from each binomial queue. We will illustrate this process by merging the orange with the purple binomial queue shown in the slide. To begin, we merge the binomial tree B'0 from the orange binomial queue with B0 that comes from the purple binomial queue. Merging these two B0 trees results in a B1 tree, which is shown in blue and labeled as B'1. Assuming a max heap, when merging two binomial trees, the tree with the smaller root should be attached to the larger tree root as a subtree. In a min heap, the opposite is true. This merge order ensures that the heap order property is preserved in the merged binomial tree. For example, since the root of B'0 has a smaller value, it is attached as a subtree to the root of B0. As a result, the merged binomial tree B'1 maintains the heap order property. After the merge, we have three B1 binomial trees: the purple tree B1, the orange tree B'1, and the blue tree B'1. Next, we merge two of these three B1 trees. The choice of which trees to merge can be arbitrary. For example, we can merge the purple tree B1 and the orange tree B'1, leaving the blue tree B'1 unchanged for now. By comparing the roots of two selected binomial trees, we find that the purple tree B1 should be attached to the root of the orange tree B'1 as a subtree. This merge results in a blue binomial tree B'2 shown in the slide. Next, we proceed to merge the B2 binomial trees. The orange tree B'2 and the blue tree B'2. Since the orange tree B'2 has a smaller root than the blue tree B'2, it should be attached to the root of the blue tree as a subtree. This merge results in the blue binomial tree B'3. Since we only have a single B3 tree, no further merges are necessary, and we can terminate the merge process at this point. This series of merges leaves us with a B3 tree and a B1 tree, which together form the merged binomial queue. We can verify that all data elements are included in this new binomial queue, and that each binomial tree within it maintains the heap order property. The merge of two binomial queues can be understood using the standard method for adding the binary representations of the binomial queues. Consider the orange binomial queue, which contains a B0, a B1, and a B2 tree. The binary representation of this binomial queue is 0, 1, 1, 1. Similarly, the purple binomial queue contains a B0 and a B1 tree, which can be represented as the binary 0, 0, 1, 1. To add the two binary representations, we start by adding the digits at the least significant positions and iteratively move to the more significant positions. This process mirrors the binomial queue merge operation, where smaller binomial trees of the same height are merged first, followed by the merging of larger ones. In this example, the sum of the binary representations 0, 1, 1, 1 and 0, 0, 1, 1 is 1, 0, 1, 0, with ones in the first and the third positions. This indicates that the merged binomial Q should contain a B1 and a B3 tree, which is precisely the result of the merge. Given the similarity between the binomial Q merge operation and the standard method for binary addition, they share the same time complexity. Note that merging two binomial trees involves comparing their root values and attaching one tree to the root of the other tree, both of which can be done in constant time O1. Recall that adding two m-digit numbers using the standard method requires linear time OM. Therefore, merging two binomial Qs with size n, which corresponds to binary representations with at most O log n digits, requires O log n time. Next, we claim that the insert operation can be performed in O log n time. This is because the insert operation can be viewed as merging a single node binomial Q with the existing binomial Q, a process that takes O log n time. To analyze the time complexity for the delete best operation, recall that the best element is always located at the root of a binomial tree. For example, in the binomial Q shown here, the best element, 65, is located at the root of the binomial tree B2. Let Bm denote the binomial tree containing the best element, and let H represent the binomial Q formed by all the other binomial trees except Bm. In our example, Bm is B2, and H consists of the binomial trees B0 and B1. Given the structure of the binomial tree Bm, deleting its root will result in a set of smaller binomial trees, Bm-1, Bm-2, all the way through B0. For example, deleting the root node 65 from the B3 tree shown in the slide will result in a B2, a B1, and a B0 tree. This property can also be understood through binary subtraction. For example, the binary representation of the binomial tree B3 is 1000, where only the third position of this binary has a value of 1. Subtracting 1 from this binary representation corresponds to removing the root node from the binomial tree, resulting in the binary representation of 0, 1, 1, 1. This binary representation has ones in its 0th, 1st, and 2nd positions, indicating that deleting a node from a B3 tree results in a B2, a B1, and a B0 tree. Let H' denote the binomial Q formed by these resulting binomial trees after the deletion. Given this property, deleting the best element 65 from our example results in the binomial Q H' that contains the trees B'0 and B'1. Next, we merge the two binomial Qs, H and H', which takes O log n time to complete. Merging H and H' results in the binomial Q shown here. You can verify that all remaining data elements after deletion are included and correctly positioned within this binomial Q. Next, the increase key and decrease key operations can both be performed in O log n time. Since binomial trees are valid heaps, value changes can be accommodated through percolation. The time complexity of these operations is therefore bounded by the height of the binomial trees. As established in our previous analysis, the height of the largest binomial tree is in O log n. Therefore, both the increase key and decrease key operations can be performed in O log n time. At last, let's examine the construct operation. Recall that in the previous video on leftist heaps, we established that any heap data structure supporting O log n merge operations can be constructed in linear time On using pairwise merge. In this case, a binomial queue can also be constructed from a set of n unsorted elements in On time. To summarize, the time complexities of fundamental operations for various heap data structures are listed in this table. The regular binary heap is a complete binary tree implemented using an array, which ensures efficient data storage and access. However, merging two binary heaps requires On time. To improve merge efficiency, we introduced the leftist heap and skew heap data structures. Compared to the regular binary heap, they reduce the time complexity for the merge operation to O log n, but increase the increase key and decrease key operations to On time. Finally, the binomial queue supports merge, increase key, and decrease key operations in O log n time. However, its find best operation now requires O log n time. It is important to know that leftist heaps, skew heaps, and binomial queues must be implemented using nodes and pointers, leading to higher memory usage and longer data access time compared to regular binary heaps. In conclusion, the choice of heap data structure should be based on the frequencies of different heap operations. This concludes our discussion on the heap data structures. Thank you for watching and see you next time.